Communication is the sending of a message from an emitter to a receiver, and that message is transmitted through a medium of some kind or another.
Animals have evolved many ways to send messages through various media such as body movements, sound, scent production, or morphological features that carry important information to others. Although an important first step in evaluating animal communication is to identify the medium that's being used, it's not always clear who is the intended recipient of this information, nor what it's meant to mean to them when they actually get the message.
If we look at a frilled lizard darting around on a rocky territory and flashing these fancy neck fans, it seems intuitive that there's a message. But for whom? And for what purpose? These answers may come with proper observation of their communicative behaviors and to see when and where they send these messages in their daily routines. It may turn out to be a territorial threat to a male of its own species, or perhaps a response to a potential predator lurking nearby. However, another thing seems to be clear about this form of communication, that it involves a series of complex behaviors alongside highly evolved morphological structures. It is unlikely that this full array of communicative features evolved all at once for the purpose of sending their message. It's more probable that the frills and the lizard behaviors evolved cumulatively over time for other reasons, like thermoregulatory ones, or perhaps for the courtship effects. It's hard to know because we weren't there in the evolutionary past. Presumably, though, there would have been rudimentary forms of these features in the distant past that didn't play communicative roles, and that the animal communication evolved out of pre-existing traits that evolved for different or incidental reasons. Piecing together the evolutionary story of the origin of communication behaviors is still one of the great challenges in the study of animal behavior. If we observe spotted hyenas greeting each other in the wild, we would probably recognize the anal genital sniffing that is also common to cats and dogs as a way of sussing out each other's hormonal status. For social animals that live in packs, knowing the hormonal state of the other individuals can provide valuable information about dominance and subordination in the group, and to know one's place in the social hierarchy. An interesting feature of this social greeting in spotted hyenas, however, is that it also involves the display of a long and dangly appendage in the genital region. Now, I'm not being shy or embarrassed to say penis, because that's not what it is. The hyenas in question are female, and that dangly appendage, therefore, is a fake or pseudo-penis that those females have evolved to be included in their communicative presentations to one another. It would certainly be normal for a field biologist to have a WTF moment upon discovering that the female spotted hyenas are sporting fake penises. But once the excitement wears down, the mystery remains as to how and why a pseudopenis could evolve to contribute to inter-female communication among these hyenas. There must be a logical explanation. From a developmental point of view, male and female genitalia are identical during early embryological stages of all mammals. The original nub, known as a genital tubercle, will either extend and turn into a penis in males, or remain short and become the clitoris in females. Apart from the genetic differences in the male and female fetuses, the hormonal environment of the womb will also impact on the sexual development of the young. For example, increases in testosterone will have important masculinizing effects on female sexual development, just as higher levels of estrogen can lead to feminizing effects on the sexual development of male mammals. When researchers studied the hormonal profile of female spotted hyenas, they found extremely high levels of testosterone during gestation, which could be the reason that the female cubs would have a seriously masculinized clitoris that resembles a penis. Although this proximate mechanism may make sense as to how this morphology came about, it doesn't quite describe why this has been selected for and remains a feature of these female hyenas over evolutionary time. If there wasn't an extremely beneficial effect of having these pseudo-penises, then they would be deemed highly maladaptive and selected against over time. This is because the pseudopenis is also the birth canal for the females, and this leads to massive challenges for reproducing. You may have heard that birthing of human babies is difficult, with expressions like trying to pass a football through a garden hose being aptly descriptive. However, for the female hyenas, it may be like passing a softball through a drinking straw, and it is not guaranteed to work out. Approximately 10% of female spotted hyenas die upon their first attempt at reproduction, and overall around 60% of firstborn cubs will die in the process as well. These are extremely high fitness costs to pay for this feature, so there must be equally high benefits to justify its existence in the first place. When we look at spotted hyena societies, they are matriarchal, with females leading the pack and with strong social hierarchies among them. Those females that have the highest levels of testosterone benefit by being more aggressive and enjoying higher social standings that bring about advantages like first feedings on the collective hunts and prime choices for mating opportunities. Likewise, those fitness benefits from high-ranking and aggressive females are inherited by their daughters as they develop in the testosterone-rich womb of their mothers. It appears that the adaptive feature among female spotted hyenas could be the aggressive behavior brought about by higher than average testosterone levels and not the pseudopenis itself. In this case, the pseudopenis would simply be a side effect of the selection for higher testosterone levels in females, and over time would also act as a proxy in conveying important messages to others in the pack about hormonal status and social dominance. This allows us to note that the evolution of a communicative medium does not necessarily need to be directly evolved for it to work. It could be a useful byproduct of selection for another feature that itself is highly adaptive. When the environment is highly variable and information about the location of food is crucial to an animal's survival, we sometimes find that complex communication can evolve in even rather simple animals. Honeybees are social animals that live in large colonies made up mostly of sibling workers that collect food from flowers and bring it back to the hive to feed the rest of their family within. When one worker bee finds a rich patch of flowers with plenty of pollen and nectar, she will hurry back to the hive to communicate its whereabouts to the others. Through the action of a simple dance involving some excited waggles and a directed figure-8 dance routine, these worker bees are able to communicate the precise location and quality of flower food resources outside the hive to recruit enough worker bees to go out and forage the nectar and pollen. The waggle dance, as it is known, not only recruits other workers to help collect the food from outside, but it precisely indicates how many workers would be required by describing the amount of food resources available, as well as which direction and how far it is from the hive entrance. This large amount of information is all coded into the complex waggle dance. Through the intensity of the waggle, the distance danced during the waggle portion, the angle of the waggle pieced to the sun from the entrance door, and finally, the overall duration of the waggle dance itself. Of course, this complex communication is highly adaptive to the colonial honeybees, as it allows them to share knowledge about food resources and to work collectively to harvest them. However, given the multiple units of information contained within the dance communication, we must assume that it had evolved incrementally instead of all at once. In fact, if we look at other types of bees that are not as socially advanced as the honeybee, we do find intermediate forms of dance communication, such as a simple round dance that acts as a recruitment communication but does not contain any directional or distance information. Other groups of bees have a dance that communicate distance with no direction information, and so on. We can see these intermediate forms of dance communication as possible examples of the process by which the communication behavior may have become increasingly complex over time until it reaches the zenith of precision in the honeybee's waggle dance. Every animal is wired slightly different via its nervous system. This can lead to important sensory biases, in which animals experience the world differently through their own unique senses. This pre-existing sensory bias can also be a source for the basis of communication behavior. We can see this in Trinidad guppies, whose males are chosen for mating by females in part due to the amount of orangeness they display on their skin. Orange color in animals is produced by carotenoid pigments, which cannot be synthesized by animal physiology and must therefore come from the diet. In the tropical streams of Trinidad, where these guppies live, many orange fruit fall into the water from nearby trees and represent important food sources for the fish in those streams. It has been hypothesized that the female guppies are attracted to the orange spots on the males because they had a predisposition to liking the color orange, given the payoff received when seeking out orange food in their environment. Over time, the orange message from the males would persist, not only because it tapped into the innate preference of the females to orangeness in general, but also because it allows the females to evaluate aspects of male quality at the same time. Carotenoids often come with many health benefits to animals, including antioxidant effects, and a male animal that displays lots of orange tissues is also announcing that they're in good health with a strong antioxidant-powered immune system. But guys, if you're thinking about painting it on, sorry, it's been tried and it doesn't work. To test the orange bias in female guppies, field researchers measured the degree to which the female fish would peck at orange discs and compared it to their preference for orangeness in the males. They found a strong correlation between the intensity that females sought out orange food and their degree of preference for orange males, which suggests that the sensory bias is in fact playing a role in the origin of this mating communication strategy. In both cases, a preference for orange would be adaptive because it would come with food payoffs in one instance and mate choice benefits in the other. It's an evolutionary win-win. Although we've been emphasizing up until now that most communication behaviors did not simply evolve out of nowhere, that they were built incrementally over time, or that they were based in some kind of pre-existing sensory bias, for example, this is not always the case. It is true that in some instances, new forms of communication can simply appear out of nowhere, so to speak. Of course, it would not be from nowhere, technically speaking, but rather from a novel genetic mutation that produces a brand new phenotype, where none existed beforehand. Despite being relatively rare over evolutionary time, novel mutations can sometimes be adaptive and become selected for in the blink of an eye. Evolutionarily speaking, that is. For example, although head crests are common in many kinds of birds, like cardinals and blue jays around these parts, the Australian finch lineage has never evolved a head crest. However, when biologists experimentally glued a feather to the forehead of male birds, it had the effect of instantly getting a reaction from the female finches. Interestingly, the color of the feather had a strong impact. When the males received a glued-on red or green feather, the females were not impressed. However, when males received a white feather glued to their forehead, they became 3 to 4 times more attractive to the females. Whereas color did have an effect, which implies that there may be some kind of sensory bias preferences built into this scenario, it is clear that if a mutation were to spontaneously create white crest feathers on the foreheads of male Australian finches, that it would be a highly adaptive, novel form of communication that appeared to come out of nowhere. The random nature of mutation effects is such that most of them are usually harmful and selected against. But this elegant study shows quite clearly that it is possible for mutations to lead to a rapid selection for novelty and to contribute to the adaptive communication between animals. When we look at inter-male conflicts, there can be many, as it is common for male animals to roughhouse with one another as they fight for access to territories or resources or female mates. There certainly are benefits for the winners of these bouts, but they inevitably come with costs of expending time and energy that would be best spent elsewhere in their lives. In the worst cases, they may even get one injured or killed. Because of these high costs to the male-male rivalry, a number of behaviors have evolved to try to reduce their impact on the individual males involved in these confrontations. What we see is that communication can play a very important role in defusing unnecessary scuffles between competing males. When a male European toad is accepted for mating by a receptive female, he will mount on her back in a pre-mating position, known as an amplexus, and will defend her against any challenger males until she lays her eggs in the water for him to fertilize. If she is a large and high-quality female, the mounted male may have many intruder males coming and looking to dismount him and take their position on the amplexus throne. One of the first things that an incoming male will do before engaging the mounted male is to let out a croak. Brrr. And the other croaks back. Brrr. Strangely, in some circumstances, this initial croak-off leads to the intruder backing away and giving up. And at other times, he persists with his attempt to dethrone the resident mounted male. What exactly is being communicated in that croak that can determine the future of the challenge? It turns out that the frequency and volume of a toad's croak can be used as honest signals of their quality, because only large and strong toads can make a deep and loud croak. This is simply a physical limitation that they cannot fake, because it is related to the size of their vocal cords and lungs, which are both proportional to their overall body size. So, by comparing croaks, these rival males may be able to predetermine who would end up winning the fight, and allowing the eventual loser a chance to back away before they end up paying a higher price than necessary. The honest signaling of croaks is an adaptive strategy that allows male toads to assess their male-male situations and to invest only in challenges that they have a chance of winning. The challenging toad benefits from this communication by thinking, "Phew, I'm glad I didn't get involved with that guy," or "Brrr, I would have got hurt." And the mounted resident toad is thinking, "Brrr, thanks for not wasting my time and energy, pal." And again, this communication is adaptive to both parties involved. Another win-win. Another important form of communication is the one between parent and offspring. It is usually something along the lines of, feed me, take care of me," from the offspring, and yeah, I'm doing my best, kid," from the parent. Upon closer inspection, we can note some nuances, however, and that communication is being done as adaptively as possible. We often observe a nest full of chicks that are silent until the moment a parent returns with food, and then the cacophony of chirping begins. The chicks frantically call for a feeding while the parent is distributing some regurgitated worms or insects. But once the parent leaves, the chirping quickly comes to an end, and the blind and bald chicks settle down into the bowl of the nest in silence. If we think about the begging behavior of these bird chicks from an economic or optimality perspective, we would assume that the benefit of this communication behavior is that it would get the chicks fed by the parent. But it would come with costs as well, such as alerting nearby predators of their location. Although the potential cost of discovery by predators is just as real whether the parents are at the nest or not, there are no benefits to chirping when the parents are away. This simple shift in the cost-benefit aspect of the begging behavior explains the stark difference in the amount of begging when the parents are there versus when they're away, and why they keep shut when no food or protection are around to ensure their survival. Clearly, there can be some instances where the benefits of making loud begging noises may outweigh the potential costs, but the threat from predators is real and always on the radar. For some bird species, the threats from predators are higher because they nest on the ground, where foot traffic is high compared to being up on the end of a single branch high up in a tree. This increase in danger for ground nesting bird species would have the effect of shifting the cost-benefit ratio of making loud begging noises, unless the benefits could be increased in tandem with the costs. Unfortunately, that's not quite how evolution works, but it does tend to find ways to decrease the costs when they can become too high. When we study the sounds of the begging chirps coming from chicks in ground nesting bird species, they're typically found to be at a significantly higher frequency when compared to the begging chirps from tree nesting species chicks. This would make sense when you consider the physics of sound propagation. Simply put, higher frequencies of sound do not travel as far as low frequencies do, so they would not be heard as well by potential predators. This is particularly true in a forest, where there are many layered obstacles like branches and leaves that act to filter out the higher frequencies first. If you think about it, we experience this phenomenon on an annoyingly frequent basis. When you see a souped-up car with neon lights, giant rims, and an obnoxiously loud muffler, there's usually one other feature that precedes the visual assault. That of the bass in their loud music that they're blasting inside the car. Boom, 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 goes the low end of the dance track. And that's all you usually hear. You could say thankfully, I suppose. But it really is a physical phenomenon where the high end is getting filtered out by the obstacles, like the car itself and the density of its occupants. And I do mean density. Now, back to the chicks chirping in a forest. If a higher frequency is less detectable, then it would certainly be evolutionarily adaptive for the ground nesting species to adopt these higher frequencies, and they do. Between different animal species occupying similar ecological niches, we see that the costs and benefits of certain behaviors can differ in the differing contexts. Evolution usually has a way of reducing potential costs when they can be high, so the behaviors can continue to be adaptive in a range of different environments. When sound is used by animals to communicate with one another, the emitter of that sound presumably has an intended receiver for the communication to work. However, sound does not discriminate from one hearer to the next. That old proverb of a tree falling in the forest forgets to take all the many animal species around that will in fact hear it fall. The same is true of intimate communications, like those between a chick and her bird parent, where there's a good likelihood of having all sorts of illegitimate receivers of those sounds. If it happens to be a predator, the consequences of those personal communications being eavesdropped upon makes the concept of illegitimate reception a true threat to the senders of those sounds, especially if they're blind and helpless chicks. Having private communications intercepted and used against oneself is one challenge for animals trying to communicate with one another. But the ruse can go both ways. Illegitimate signalers are those that are sending out mixed messages in an attempt to trick its receiver into believing it's false messages. Fireflies of the Photinus genus use flashes of bioluminescent light to communicate courtship messages prior to reproduction. Males have a species-specific series of light flashes that are produced by an enzymatic reaction in his abdomen as a courtship demonstration for the females, who are watching from a small distance away in the dark. If she becomes impressed by the light dance of a particular male, she will flash a few short bursts of light to help him find her for mating. Unfortunately for the male Photinus fireflies, there are dangerous imposters signaling from the dark as well. In a distantly related genus, the female Photurus fireflies are predatory of the smaller Photinus males. As the Photinus males are flashing about and trying to court the females of their species, a femme fatale from another species is flashing back and mimicking the sexually receptive nature that he is seeking. Only that instead of arriving at a female of his species that is ready to mate, he will become food for a larger predatory rival. Only because the drive to find a mate is so strong, and that the illegitimate predatory signalers are a minority in the grand scheme of things, do we find that these deceptive communication interceptions can work over evolutionary time. If male Photinus fireflies stopped responding to receptive female flashes, that would spell disaster for the continuation of the species. Thus, this code breaking by the devious and cunning Photurus females can continue to persist by luring unsuspecting males to their death.
Like other behaviors, communication has evolved as an adaptive trait. In this case, to convey crucial information that's biologically relevant to others. And like other adaptive traits, communication most likely did not evolve all of a sudden out of nowhere, but was rather built upon over evolutionary time through the processes of adaptive selection, constantly refining and improving the clarity of the messaging in the communication between animals.
Sometimes it works in your favor, and sometimes, well, not so much. But if it works more often than not, that communication will contribute to the species' fitness and persist.